Experiment 16 deals with the volumetric analysis of redox titration. What we'll be doing in this experiment is similar to the acid-base experiment we did in experiment 13, which we're dealing with the unit of normality. And normality, you may recall, is equivalent weight of solute per liter of solution. Now, when we did the acid-base titration, the number of equivalents was equal to the number of hydrogen ions or hydroxide ions ionized. So it's pretty simple looking at how many H pluses or H minuses was given up. There's no balance in the equation needed because we can use NV equals NV because that equivalence is within the whole unit of normality, so we don't have to write a balance equation. We'll be doing the same thing except we're not dealing with acids and bases. This time we're going to be dealing with a redox reaction, which involves the transfer of electrons. Redox stands for reduction oxidation reaction. Now, this is a little bit more difficult than acid-bases because what you're going to have to do is write a half reaction to figure out how many electrons are being transferred, and that number of electrons is going to give you a number of equivalents per mole of substance. So we're going to have to refresh our memory on how to balance redox to be able to figure out the number of electrons, to be able to do your normality, and then use your NV equals NV. In a redox reaction, the definition of equivalent weight will be one equivalent of any oxidizing agent reacts with one equivalent of any reducing agent. Contrary to what the acid-bases, we were dealing with number of protons and hydroxides. So here we'll be looking at equivalence of our oxidizing agent versus equivalence of reducing agent. What this boils down to is the number of equivalents per mole is equal to the number of electrons transferred. So you're going to have to write a balanced half reaction to determine the number of electrons being transferred. Here's an example. Permanganate plus 8 H pluses plus 5 electrons gives me manganese 2 plus 4 water. This is your net ionic equation. The spectators have already been removed. From this, we can determine the number of equivalents for the substances. This 5 electrons is telling me the number of equivalents per mole of whatever substance we're talking about. So if I'm talking about permanganate, okay, which there's 1 mole of permanganate in this equation, then that tells me there's 5 equivalents for every 1 mole of permanganate. If I was talking about hydrogen ions, it'd be 5 equivalents per every 8 moles of hydrogen ions. I got to account for that number of moles. Now we got to go from that to our primary substance, which possibly with the spectator would be potassium permanganate. There's a 1 to 1 mole ratio between potassium permanganate and permanganate ion, which basically means there's 5 equivalents for every 1 mole of potassium permanganate. Another example, let's look at iron 2 going to iron 3 plus 1 electron. Once again, that number of electrons tells me the number of equivalents, and I can do that for whatever species. In this case, let's look at iron 2. There's 1 equivalent for every 1 mole of iron 2. Now notice in both examples we did here was per 1 mole basis. That's not always the case, as I mentioned about the H pluses. And then in our particular experiment for this experiment, we don't have a 1-to-1 in one of the species as well. So you got to account for that number of moles. Let's look at going from normality to molarity or molarity to normality. We know that normality is equivalents per liter, and we know that molarity is moles per liter, so all we need is a transition between moles and equivalents, which is that equivalence weight. We know that there's a certain number of equivalents per mole from that balanced half reaction. If we do that, we multiply molarity times that equivalent weight, the number of equivalents per mole, we see that moles cancel, leave me in the number of equivalents per liter, which is normality. One thing to keep in mind when you do these calculations between molarity and normality to know if you're doing things correctly is that normality will always be equal to or greater than the molarity. So normality will be equal to molarity if it's a 1 equivalent per mole ratio, or if it's something greater than 1 per mole, 1 equivalent per mole, then normality will end up being greater than that molarity. Let's do a calculation. Let's try to convert 0.1 molarity potassium permanganate into normality. So basically our goal is the number of equivalents of potassium permanganate per liter of solution. To do this, we must have a balance half reaction, which we already did on the previous slide, which looks like following. You got permanganate plus 8 pluses plus 5 electrons gives me a manganese 2 plus 4 waters. That 5 electron is telling me the number of electrons being transferred, and I can use that in relation to the species of the permanganate, which tells me there's a 5 equivalents per every 1 mole of permanganate, or in terms of what we're looking for is potassium permanganate, there's a 1-to-1 between permanganate and potassium permanganate. Therefore, we know that the equivalent there is 5 equivalents per every 1 mole of potassium permanganate. So the calculation then would look as follows. We start off with our 0.1 moles per liter of potassium permanganate. That's what I'm trying to convert into normality. I need some conversion factor, which we know is there's 5 equivalents for every 1 mole of potassium permanganate. I'm going to put that in relationship to get the moles to cancel. So next I will have my 5 equivalents per 1 mole of permanganate. Therefore my moles cancel out, leave me in equivalents per liter, which then gives me 0.5 equivalents of potassium permanganate per liter. Or putting it in terms of equivalents per liter, the symbol for that is capital N, so it would be 0.5 capital N, meaning normality, potassium permanganate. Notice that the normality is greater than the molarity. Okay, it's always going to be equal to, if it's a 1-to-1, or greater than the molarity. To be able to handle these type of problems, we're going to have to be able to balance redox equations. So let's go back and refresh our memory about how to balance redox equations. Now, there's a few facts we're going to have to know to be able to do that. We've got to know solubility rules, know charges, know how to write an ionic equation, those type of things. So we're going to refresh our memory on those things, then actually balance some redox equations, and then move on to the rest of this experiment. One of our goals is to balance a redox equation, and to do that you need to know some knowledge. Okay, you have to have some knowledge on different things. One of the things you have to know is solubility rules. Okay? The solubility rules are based on information gathered based on size and charge of the different species. And basically we're sticking a compound into water and we're seeing if it dissolves. Okay, by definition, if it dissolves and makes greater than 0.1 molarity of solution, then we refer to it as a soluble solution. And we basically, a soluble compound rather, and it has, we tend to put an AQ behind it when we write the name of that formula. If it dissolves and it forms solutions that are less than 0.01 molarity, we refer to it as insoluble, and we tend to put an S behind it for solid behind the name of that compound. If it's in between 0.01 and 0.1, then we refer to it as slightly soluble, and it depends on pH and other factors. But for this case, this class, we're going to tend to just call it, if it's slightly soluble, we're going to call it soluble. Okay, so what are the solubility rules? First off, all compounds containing alkali metal cations, which are your group 1 metals, okay, and the ammonia ion are soluble. 2. All compounds containing nitrate, perchlorate, chlorate, and acetate anions are soluble. So if those anions attached to anything, it's soluble. 3. All chlorides, bromides, and iodides are soluble. However, there are some exceptions, okay? Those containing silver, lead-2, and mercurous ions are insoluble. Okay, so the majority of them are soluble, but there are a couple of exceptions. All sulfates are soluble, except those containing mercurous, lead-2, barium, strontium, or calcium. Okay, so most of them are soluble, with a few exceptions. And silver sulfate is slightly soluble, so we're going to consider it soluble. All hydroxides are insoluble, except compounds of the alkali metals, that's your group 1, and calcium, strontium, and barium, which are slightly soluble. Okay, the hydroxides are your strong bases. Okay, the soluble ones are the strong bases. Okay, that's your alkali metals and your calcium, strontium, and barium. 6. All other compounds containing phosphate, sulfide, carbonate, chromate, sulfite, and most other anions are insoluble, with exceptions, going back to Rule 1, the alkali metals and your ammonia compounds. Okay, now that we know the solubility rules, let's see if we can use those to figure out if it's going to be an insoluble or soluble salt and how we represent that. Let's look at one example. Let's look at mercurous chloride. According to the solubility rules, all chlorides are soluble with some exceptions. This is one of those exceptions. This is mercurous chloride. So this is one of those insoluble compounds. So to represent that, we'll use an S for solid. Let's look at another example. Potassium iodide. Okay, potassium iodide is going to be a soluble salt for two reasons. Number one, potassium is an alkali metal, which we said all alkali metals are soluble, and iodine is all iodines are soluble with the exceptions of silver, lead, mercurous, and it's not one of those. So in that case, in both cases, it is a soluble salt. So we represent that with an AQ for aqueous. And lastly, let's try lead 2 nitrate. There's lots of exceptions in the rules about lead. However, this is a nitrate, and Rule 2 states all nitrates, doesn't matter what's attached to, all nitrates are soluble. So this, even though it's lead, it's still a soluble salt, and we use AQ to represent it. Another important thing that you must know, well, what are the strong acids and bases and what are the weak acids and bases? Okay. Another important point you got to know is what does it mean to be strong and what does it mean to be weak. Okay, when we say something strong, we're saying that it ionizes 100%. Okay, it ionizes 100%. So if I have HCl, which is a strong acid, it breaks up into hydrogen ions and chlorine ions. We're saying that if I had a 1 molar solution of HCl, it will break up 100% and form those ions. 1 molarity of H plus, 1 molarity of Cl minus. There's no HCl as a whole. Breaks up 100%. Contrary to something like hydrogen cyanide, which is a weak acid, it ionizes less than 5%. Okay, so the majority of that species stays as HCN, and only a small fraction forms the H plus and the Cn minus. Okay, and that's the difference between strong and weak. Strong, 100% ionization. Weak, very little, less than 5%. So how you learn the strong acids? You memorize these 6: HCl, HBr, HI, HClO4, HNO3, and H2SO4. You learn these acids as your strong ones. All other compounds that start with hydrogen first are weak acids. Okay, so learn the strong ones, and then all the weak ones will be everything else. The bases. Strong bases tend to dissociate 100%. Same thing. Bases break up 100%. Weak bases do not. Okay, strong bases are your group 1 hydroxides and your barium, calcium, and strontium. So sodium hydroxide, potassium hydroxide, lithium hydroxide, barium hydroxide, calcium hydroxide, and strontium hydroxide. Now the weak base is a little more difficult. It's your ammonia compounds, ammonia type compounds, NH2 somethings on NHs, NH3 for ammonia, and then your anions. Okay, the anions of your species also can be basics. For example, CO3 2- carbonate ion, that's a base. Okay, something like sodium carbonate is a basic solution. But we'll talk more about that as we go on in the semester. The ultimate goal is to do a balancing of a redox equation, but before we can get there, we're going to learn how to write regular equations. So the first thing we're going to talk about is molecular or formula unit equation. Okay, this is one in which the reactants and products are written as if they were molecules or formula units, even though they may actually exist in solution as ions. So it's not how it is in solution, it's basically its formula unit. It's your normal balancing equation that you've done back in Gen Chem. Okay, you're writing your reaction and balancing it off and putting the states as well. So let's look at an example. Let's look at calcium hydroxide and sodium carbonate. Okay, I'm going to write the molecular equation of this. First off, you're going to be able to write substances into their formulas. So we got calcium hydroxide. So calcium is a 2+ charge, hydroxide is OH-. So I need to balance that off within that whole formula. So it ends up being Ca open parentheses OH, close parentheses subscript 2. That's calcium hydroxide. We're going to add that with sodium carbonate. Sodium is a +1. Carbonate is a CO3 with a 2 minus. Therefore, it's going to take two sodiums to balance out the charges. So I get plus Na2CO3. Now, what I'm trying to do now is write my products. Okay. Typically, reactions could be displacement combinations, several options, okay? But we're talking about some molecular substances here, ionic species. So basically, displacement will happen 90% of the time. So all I'm going to do is take the cation in one species and displace the cation in the other. In this case, I'm looking at sodium, and it will displace calcium, and then calcium will displace sodium. Now, one thing to keep in mind is when we're doing that, we don't bring the subscripts that we use to balance the previous formula. We will bring the entire polyatomic ion, OH minus, or CO3, 2 minus, okay? But we're not going to bring any subscripts such as this 2 and sodium. That was there to balance this substance out, so we will not bring that with it. So if I do that, I will get calcium combining with CO3, okay? And then I'll also get sodium combining with OH. Now we have to balance the substances between these species that we just put together. Calcium is a 2 plus, CO3 is a 2 minus. That's already balanced, so there's no subscripts needed to balance that out. Sodium is a +1, OH minus is a -1. Therefore, there's nothing needed to balance that. So although the substances are balanced, calcium carbonate and sodium hydroxide, the whole equation is not balanced yet, so we need to balance that. Looking at it, you can see I need 2 sodiums and 2 hydroxides on the product side to balance this out, so I'll put a 2 in there. And you can see now I have 2 sodiums on both sides, I have 2 hydroxides on both sides, 1 calcium on both sides, and 1 carbonate on both sides, give me a balanced equation. But that's not the complete picture. You also need to put in the states, okay? So we're going to have to put in things like, if it's a solid, insoluble salt, some salt, we're going to have to put an S behind the substance. If it's a liquid, L. If it's a soluble species, meaning the acids and bases are soluble salts dissolved in water, then we put AQ for aqueous. Now that doesn't mean 100%, and that just means it dissolves in it. Okay, we're not talking about ionization here. We're just talking about dissolving. So all species that dissolve will be AQ, and G will be used for gases. Okay. Now we're going to make a decision of which one of these we're going to use behind these substances. Let's look at calcium hydroxide first. What kind of species is calcium hydroxide? That's one of the strong bases. Okay, what happens to a strong base? It's soluble in water. Therefore, we're going to have to represent that as aqueous. What about sodium carbonate? What kind of substance is that? That's a soluble salt. Okay, since it's a soluble salt, it's going to dissolve in water, so we're going to call that aqueous. Calcium carbonate. Okay, what kind of substance is that? That's an insoluble salt. Insoluble salt, then we're going to have to refer to that as an S for solid. And sodium hydroxide, that's a strong base, so it's a soluble species, therefore we will refer to that as AQ. This is our balance equation, including states. This is important, especially when you start trying to do redox equations, etc. You need to figure out how things are going to react in water, and will they dissolve, will they not dissolve, will they ionize, will they not ionize. You need to know these kind of facts to make decisions. Another type of equation that we have to discuss is the total ionic equation. This represents strong electrolytes as separate independent ions. This is a more accurate representation of the way electrolytes behave in solution. A complete ionic equation is a chemical equation in which the strong electrolytes, strong meaning your soluble ionic compounds, and your strong acids and bases, are written as separate ions in solution. Okay? Your gases, your liquids, insoluble salts, weak acids, and bases do not break up and are not ionized in your total ionic equation. Let's continue on with the example we've been using. We already discussed what type of substances they are. So let's look at calcium hydroxide. That is a strong base. What happens to a strong base when we place it in solution? Well, it ionizes 100%. That means that the calcium hydroxide will break up into ions. The calcium will ionize to calcium 2 plus. The hydroxide will be OH minus. Now this subscript 2 tells me how many are going to be there. Okay, realize it's two OH minuses. It's not OH with a subscript 2. Okay, it's a hydroxide, and that tells me how many. So it ionizes into calcium into OH minuses. Sodium carbonate, we said, is a soluble salt. What happens to a soluble salt? It ionizes 100%. So once again, we break this into ions. It'd be 2 sodium ions and 1 carbonate ion. Then we have calcium carbonate, which we said was the insoluble salt. What happens to it? Well, it stays as a whole. Okay, so we'll bring that down just like it is. And lastly, we have sodium hydroxide, which is a strong base. Once again, ionizes 100%, so we break that into 2 sodium ions, 2 sodium pluses, and 2 hydroxide ions. It's 2 for the whole thing of NaOH, so I got to count for that in both of these ions. This is our total ionic equation, which we need to do this step before we move into the next step, which is your net ionic equation. Net ionic equation is a chemical equation from which the spectator ions have been removed. Okay, spectator ion is an ion in an ionic equation that does not take part in reaction. Just like a spectator at a football game is watching the event, it's not part of the football game. Spectator is not part of a chemical reaction. It's just watching the chemistry go on elsewhere. Many times they only give you the net ionic equation, and you can use that. You use that for your calculations. They don't even give you the spectator ions. So, what we mean by a spectator is something like if I had sodium ion, aqueous ion on my reactant side, and a sodium aqueous ion on my product side, it's exactly the same. It hasn't changed. That would be a spectator. If I have H plus as ion on one side and water on the other side, well, H plus is changed as an ion to part of the water molecule. That's not a spectator. There's some chemistry that has happened for that to happen. So we only get rid of those things that nothing changes. So going back to our previous example, looking at ionic equation, let's look at calcium. It's 2 plus ion on the reactant side. On the product side, it's part of calcium hydroxide. Well, there's chemistry going on. It's not exactly the same anymore. Ca2 plus is now part of a molecule, okay, a formula unit of calcium carbonate. So that's that's going to go down into net ionic equation because it's not a spectator. So I have calcium 2 plus go into calcium carbonate on the product side. Let's look at hydroxide. Now I have 2 OH minuses on my reactant side and I have OH minus on my product side, so it has not changed form at all. Therefore, I will cancel that out as a spectator ion and not bring that down in my net. What about sodium? Well, it's sodium ion on my reactant side and it's sodium ion on my product side. So once again, that's a spectator. Therefore, I'll cancel that out. And lastly, we have carbonate, which is an ion on the reactant side, but on the product side, it's part of calcium carbonate. That's chemistry, so therefore we'll bring that down. If I've done everything correctly up above, then my balance equation can continue on, and my net ionic equation should be balanced just as well. This is my net ionic equation. Calcium is formed with carbonate to form calcium carbonate. That is the chemistry going on. The rest of it is just spectators, and nothing's going on chemically with those species. This gets us to the major topic we're trying to talk about is balancing of redox, so we need to discuss what a redox reaction is. By the name redox, it's a reduction and an oxidation reaction. Okay, oxidation reduction reactions involve a transfer of electrons from one species to another, so we're watching electrons being transferred. Oxidation is defined as a loss of electrons. Basically, it's losing electrons. Another way of looking at it is that it's going to a higher oxidation state. Reduction is defined as a gain of electrons. It's taking on electrons which are negative values, so therefore it's reducing. Okay, oxidation state in this case will be lower. It'll go to a lower oxidation state. For any redox reaction, you need both parts. You need something to be oxidized and something to be reduced occurring simultaneously. You can't have an oxidation going on if you don't have reduction. You need both parties to be happening. Now, sometimes we break it down into half reactions, only worry about one part or the other, and then bring it together to balance the whole equation, etc. But you have to have both parties to do a redox reaction. All right, let's talk about reduction. Reduction can be looked at in terms of a gain of electrons, taking on electrons. Could look at it as a gain of hydrogens that's related in that electron aspect, or a loss of oxygens. Here's an example. I got iron 3 going to iron 2. Okay, anytime we're talking about a reduction, the electrons will be on the reactant side. Okay, you can see it went from a +3 to a +2, and that's going to a low oxidation state. That is a reduction. Anytime we talk about a reaction, we have to balance the atoms as well as the charges. Okay, you can see you got one ion on both sides, but what about the charges? Well, I got a 3+ and I have 1-. 3+ and 1- gives you a +2. So this whole reactant side has a +2 charge. The whole product side has a +2 charge. That's balanced. Got to balance atoms as well as charges. Oxidation can be looked at as loss of electrons or loss of hydrogen or gain of oxygen, which gets back to the old definition of oxidation. Just the word oxidation gives you an indication that it's being oxidized, meaning gaining oxygens. Okay? We're using the same equation we just did before, but we flipped it now. I got iron 2 going to iron 3. It's going to a higher oxidation state. That's an oxidation. Anytime we're dealing with oxidation, you can have electrons on the product side. Okay, it's producing electrons. Once again, +2 charge on this side +3 and 1-. Okay, therefore we have a +2 charge on this side balancing the charges. What I have below here are 2 examples of half reactions. Let's see if we can figure out if it's being oxidized or reduced. If you look inside of water here, H hydrogen is a +1. Okay, that's part of that molecule of water to get that to balance out. If you look at hydrogen on the product side, it's a +1. So the charge hasn't changed. It's +1 in water and it's +1 on the product side. Therefore, there's no change in charge. Oxygen is -2 in each one of these, so there's no charge change there. The charge change has to be with this bromine. So you can see it's BrO3- and BrO4-. Well, it gained an oxygen, so that bromine has to be changing charge if it's going to both stay at -1. So we can look at that in terms of simple arithmetic. Okay, looking at that bromine, that charge has to be some number that when I add that to 3 oxygens at a -2, the total charge ends up being in excess of -1. So arithmetic-wise, I got bromine +3 oxygens times a -2 is equal to a -1. I take that -6, I'm going to add 6 to both sides to basically get it to cancel out. So I get +6. So I get -1 + 6, that gives me a +5. So this bromine here has a +5 charge. Looking at the BrO4-, do the same thing. Bromine plus your 4 oxygen at -2 gives me a -1. Bromine then is equal to a -1 + 8. Added 8 to both sides. Gives me +7. So it went from a +5 to a +7. That's an oxidation. Okay, the charge got larger. It increased. Now I could have easily decided that by looking at the number of oxygens, which goes back to the old definition, gain of oxygens. The only way that I can add 2- by adding an oxygen is that bromine has to go up by +2. So I can see that BrO3 going to BrO4-, that's an oxidation process. The second one, as you can see, I got 2 electrons on the reactant side as an indication this is a reduction. And we can see H+ is going to H2. Elemental H2 is a 0 charge, so it's going from a +1 to a 0 charge, which is a reduction. Okay. I could also look at that in terms of hydrogens. It went from an H+ to H2, so it gained the hydrogen, which is also a reduction. Some terms we need to understand is oxidizing and reducing agents. Okay, an oxidizing agent is a species that undergoes reduction. It's undergoing reduction, so it's taking on electrons, so it's allowing something else to be oxidized. Okay, hence an oxidizing agent. Reducing agent is a species that undergoes oxidation. It's undergoing oxidation, so it's giving up electrons, so it's allowing something else to be reduced. Okay, so it's called a reducing agent. So of these two examples here, let's see if we can figure out what is an oxidizing agent and what's a reducing agent. Well, since H plus is undergoing reduction, then it's an oxidizing agent. And since your bromate, your BrO3 minus, is going to go in oxidation, it's a reducing agent. Okay? Do realize that we need both to happen for a whole reaction to be a redox reaction. I got to have something being oxidized and something being reduced. These are half reactions. One's a reduction, one's an oxidation. We handle them as such, but the whole process has to happen for it to be a redox reaction. Now, to balance redox equations, you must have some knowledge. Okay, you must know the charges, the oxidation on them species, and also the polyatomic ions. All this is Chem 1 information you should know to be able to balance a redox. You must also know the strong and weak acids and bases. Okay, and that what it means to be strong. It breaks up 100%, weak less than 100%. You must also know the solubility rules. Okay, you must know all this information to be able to balance redoxes. Here's some rules for balancing redoxes. First, you got to convert the net ionic form of the equation, if it's a molecular form, and by eliminating the spectators and get it to the net. Okay, so you must convert to the net ionic equation if it's originally a molecular formula equation. You've got to eliminate the spectators. If it's already a net ionic, then you have to worry about that. But you must get rid of the spectators. Second, you write the half reactions. You write it as an oxidation and a reduction. Okay. Third, you balance the atoms. Okay. Now, if you got to balance oxygens and hydrogens, then you have H plus, OH minus, and water as needed from the solvent to make those balances. We use those depending if it's acidic or basic. If it's acidic, we have H plus and H2O. Okay, obviously I have 2 hydrogens for every 1 hydrogen here, so I'm going to put water on the side that needs the hydrogen to balance things out, and H plus on the other side. If I need to balance the oxygen, same thing. I put water on the side that needs the oxygen, and H plus on the other side to balance it out, to balance those hydrogens. Basic's a little bit more difficult. I got an OH minus and water combination. If I got to balance the hydrogens, I place water on the side that needs the hydrogens to get that balance of the hydrogens. However, if I got to balance oxygens, you can see I have 1 on both sides, so that's not going to solve my problem. So I need to fix the problem. Okay, if hydrogen's already balanced, I don't want to unbalance it, so we do a 2-to-1 ratio. Got 2 hydrogens and 2 hydrogens, balances it out. So then I'll put the OH minuses on the side that needs the oxygen and water on the other side. Now, I can balance back and forth to get things to work out. I might have to do it 2 or 3 times, or I can go directly to it and fix it from the beginning if I'm just balancing oxygens. And by that I mean I'll figure out how many oxygens I need. I'll double that many OHs on the side that needs it, add half as many waters to the other side, and I'll be balanced. Okay, I'll show you that in an example, in the last example in this chapter. Other things to keep in mind: if I only need H plus, then only use H plus. If I only need OH minus, only use OH minus. Don't complex things by adding other things to it, like water, if I don't need it. Okay. However, if you do H plus and OH minus, realize that if I find in the end I have H plus and OH minus on the same side, then that forms water. Okay. H plus OH minus forms H2O. Keep that in mind as you do these. Next, you would balance your charges for half reactions using electrons. So I balance my oxidation, balance my reduction. Okay, number of electrons as separate units. Fifth, I balance the transfer accept electrons in the whole reaction. In other words, the number of electrons in my oxidation and my reduction has to be the same now. So I multiply by some factor to make that happen. Last, I convert the equation back to the molecular form if necessary. Basically, I reapply my spectator ions. Okay, when you're balancing redox, one thing you need to do is keep a little bit of common sense as you're doing things to try to balance this out. The whole process here is to take a very difficult equation, maybe have several oxygens on the reactant side and several species that has oxygen on the product side, and you're trying to balance it out. So you're simplifying it by breaking it up into parts and then bringing it back together and balancing the whole thing. Now that we've learned the rules on balancing a redox equation, let's put it in action. And we're going to do it first with a very simple example, one that you could easily balance by inspection. You can see you easily would balance this, and you'd be a 2 coefficient in front of silver nitrate and a 2 in front of the silver solid, and be a balanced equation. But the point is not to balance equation, it is to use the procedure of balancing a redox. And I'm using this simple one just to demonstrate it. Then we will go with more complex examples as we go. On the test, if I request you to balance it by half reaction method, then you must do it by half reaction method. It's not about getting the correct balance equation, it's about the procedure, which is what I'm trying to show you here. Okay, the first thing we need to do is take this formula unit equation and now write it in a total ionic equation. That means we need to break those things up into ions that normally break up into ions, which would be your strong acids, your strong bases, and your soluble salts. So you have zinc solid first. Okay, so what we're going to do there, since it's not one of those, it will come down as this total ionic equation as zinc solid. Next thing you have is silver nitrate. Okay, what is that? That is a soluble salt. When I'm so soluble salt, it breaks up 100% into ions, which means silver ions and nitrate ions. So I would break that up in my total ionic equation. Next we have zinc nitrate. Okay, the question is, what is that? That is a soluble salt. Once again, breaks up into its ions, so we will break that into zinc 2 plus into nitrate ions. And then we have silver solid, which will come down just like it is. So we break those things that break up 100%. So you can see we have zinc, we have our zinc, and we have our silver nitrate broken up into ions. We have our zinc nitrate broken up into ions and silver solid. Now we will go from our total ionic equation to the net ionic equation. To go from the total ionic to the net, what we need to do is get rid of those spectator ions, those things that look exactly like on both sides that haven't changed state. Okay, same charge, same everything. Looking at that, we can see that there's only one species that's exactly the same on both sides, which is a nitrate ion. So those are my spectators, so I'll cancel out my nitrate ions. Now you might notice that I have a 2-to-1 ratio there. I'm not really concerned about that right now because that's the whole process of what we're doing here. We're trying to balance the equation, so that'll take care of itself later on when we go to put the spectators back on. So if we carry everything else down, we have our net ionic equation. Zinc solid plus silver ion, silver plus ions, zinc 2 ions, and silver solid. This is the start of our redox balancing, okay, and the step 2 where we have to take it and figure out what's being oxidized and what's being reduced. Okay, we're going to get to the net ionic first and then move on. Okay, now that we have the net ionic equation, we can now follow the redox rules and balance the equation. The first thing we need to do is figure out what's being oxidized, what's being reduced. So, looking at this, we see that zinc is going from a 0 charge, which is its elemental state, to a 2 plus. It's going to a high oxidation state, so that is an indication of an oxidation going on. So we bring down everything associated with that oxidation, zinc going to zinc 2 plus. We see that silver now is going from a +1 charge to a +1 charge to a 0 state. That's reduction. So we'll bring that down. So now we have silver plus going to silver solid. The next step that we need to do is to balance our atoms. Okay, it's very crucial that you balance atoms first and then move on to electrons. This is a simple example, as I stated earlier, and you can see that I have one zinc on the reactant side and one zinc on the product side. Therefore, atom-wise, it's already balanced. So I'm not even looking at charges, just looking at atoms. For the reduction, once again, I have one silver, and I have one silver on the product side. Therefore, it's balanced with atoms as well. This is where we would take into account hydrogens, hydroxides, etc., if we needed them to balance the atoms. The next step after you balance atoms is to balance charges. One thing to realize is that we have electrons, which are -1 charge, at our disposal to balance the charges. So we need to look at our charges. Let's look at the oxidation first. We have elemental zinc, which has a 0 charge. So on our reactant side, we have 0 charge for our oxidation. On the product side, we have one zinc molecule which has a 2+ charge on it. Excuse me, one zinc ion which has a 2+ charge on it. So the overall charge on the product side is 2+. 0 and 2+ are not the same, so we need somehow to balance them off. They can either be both 0, both 2+. Doesn't matter what the charge is as long as it's the same on both sides. The only thing that we have at our disposal to balance that is electrons, which are basically -1. Okay, so I need to add that to the reactant side or the product side to get this to balance out. Looking at the charges, I'm going to add 2 electrons to the product side. Okay, since this is an oxidation, it makes sense that the electron should be produced, and it should be on the product side. By doing so, now I have 2 electrons, 2 minuses, and the 2 pluses. When I add those up, that gets me 0. So now I have a balanced equation with charges. I have 0 on the reactant side and 0 on the product side. I need to do the same thing with the silver, okay, the reduction. You can see on the reactant side I have a +1 charge for my silver, and I have a 0 charge for my products. Once again, need to get that to balance, so I need to add electrons to one of the sides to get that to balance. It makes sense that I would put my electron on my reactant side, and I only need one of them to get this to balance out. So now I got 1 minus and 1 plus. That gets me 0. Once again, balance 0 on both sides. As I stated earlier, it doesn't have to be 0. Just so happens all these are 0. Okay, any charge as long as it's the same on both sides. The next step after we finish this is we need to balance the whole reaction. We handle things as half reactions first, and then we have to go back and get the same number of electrons being produced as we are accepting it. Okay, so I need to transfer the same number of electrons. We do that by multiplying the different half reactions by factors to get them to be the same. Since the oxidation is giving off 2 electrons and the reduction is taking on 1 electron, it makes sense that we will make the reduction happen twice to get those to be the same. So I would multiply the reduction by 2. That means I have 2 electrons, 2 8s, 2 silver pluses, and 2 silver solids. Multiply through by that 2 factor. Now that I got the same number of electrons, those electrons now cancel out. The electrons cancel out, and I bring down everything else. So I'll bring down that zinc solid, bring down my 2 silver pluses, my zinc 2 plus, and my 2 silvers. This is my balanced net ionic equation. Once I'm at this stage, everything should be balanced atoms and charges. If you look at it, you see that I have 1 zinc on both sides, 2 silvers on both sides, and I have a total charge of 2 plus on my reactant side and 2 plus on my product side. The last thing that we need to do is to put back on the spectators. So we need to look at each individual component and see when we add the spectators if we need to change coefficients or not. Let's look at zinc first. There is no spectators, so that will go down just like it is as in my balance equation. Then I have silver plus. Okay, the spectator on that, if you recall, was nitrate. So I need to put silver plus and NO3 minus together in their molecular formula, in their formula unit, okay, and balancing the charges. When I do that, I get AgNO3. Now the next question is, do I have to change the coefficient on silver to keep it at 2? Remember, when I balanced it, I have to have only 2 silvers. So when I put this back together, I have to only have 2 silvers. Well, since it's 1 to 1, that's not an issue. You bring it down and the coefficient is still 2. What I'm trying to say there, give you another example. Let's just say I balanced the redox equation and end up being 10 H pluses, okay, 10 hydrogen ions. And you also had the spectator ion was sulfate, SO4 2 minus. Okay, I would have to put H plus and SO4 together. Okay, when you do that, you would get sulfuric acid, H2SO4. In that process, though, I had to put a subscript on that hydrogen. Okay, I had to put a subscript 2 to balance out that substance. Okay, so when I get finished and put that in my balance equation, I got to remember I can only have 10 H pluses. Okay, so when I put that coefficient in front of the H2SO4, I'm going to put a 5. 5 times the 2 gives me 10 hydrogens. I'll still have that 10 hydrogens. Remember, I balanced the equation to make it 10. I can't change it now and put, say, 10 H2SO4s. That'll give me 20 hydrogens, which would be unbalanced in my equation. Continuing on, I have the zinc 2 plus. The spectator on that was nitrate, so I got to put the nitrate on there. It means I would have 2 nitrates on it to get that to balance out. Coefficient of 1. Putting on the nitrates doesn't change the subscripts of zinc, therefore I can just bring that down like it is, my zinc nitrate. And then I have my silver, which comes down just like it is as well. So that is my balanced equation. As I said, you could easily balance this by inspection and put the 2 in front of the silver nitrate and the 2 in front of the silver. That wasn't the point of this exercise. This exercise, the point is to use the redox balancing procedure to do it. Now we'll move on to more difficult questions where the balance using redox makes it easier. Let's look at this one. Now this is a net ionic equation, so you have no choice. You have to balance it by redox, because if you do it by inspection, you would try to put a 1 coefficient in front of the ions, and that's not going to be correct. So you have to go through the procedure here, definitely when it's a net ionic equation. Now notice there's an H plus over the arrow. That's an indication of an acidic solution. Okay, that means I have H plus and water at my disposal to use to balance the equation. So we need to look at this and see what's being oxidized and what's being reduced. Let's look at the iron first. You see that iron's going from 2 plus to 3 plus. Okay, and that's a case where it's being oxidized. It's going to a higher oxidation state. So that is an oxidation, so I'll bring that down. Let's look at the manganese and see if we can determine what's going on there. We can look at it one of 2 ways. First way, let's look at its charge. What's the charge on that manganese in permanganate? Well, you have 4 oxygens at a -2. That's a -8. Manganese minus that 8 has to equal that -1 charge on the whole polyatomic ion. Well, the only way that that can be true is if that manganese has a +7 charge. So that manganese is going from +7 to +2 on the product side. That's a reduction. You also could look at the number of oxygens. You can see MnO4 minus went from 4 oxygens to no oxygen, which is also an indication of something being reduced. So I'll bring all that down to the reduction. Now I didn't put the H plus and water anywhere yet. I'm going to let that happen as I go and balance the equation and let that dictate where to put it. The next step we got to do is make sure that we balance the atoms. Okay, we see that we have in the oxidation that we have 1 iron on each side. Okay, so there's nothing that I need to do to fix that. Let's look at the reduction. I got MnO4 minus going to Mn2 plus. You can see the manganese is balanced already. I have 1 on each side. That's not a problem. But I do have 4 oxygens on my reactant side, and I don't have any on my product side. So I'm going to need to fix that. That's where the H plus and water is going to come into effect. I need oxygen, so I'm going to place water on my product side to balance out those oxygens. Now, how many oxygens am I going to use? Well, that's coming from that 4. Okay, I need 4 oxygens, therefore I'm going to put 4 waters. So I took care of my oxygens, but in the process, did you notice what happened is we instilled a hydrogen problem. So now I got hydrogens to balance because I have none on the reactant side. No, looking at it, I ended up 4 H2Os. That means I added 8 hydrogens. So what we're going to do is add 8 H pluses to the product of reactant side. Okay, it's important to realize you have to bring the charges, okay, because we balance charges, so make sure that you add in your charges as you go through this, because we need to account for those charges. Now we have all our atoms balanced. Okay, let's now talk about charges. In the oxidation, you see that we have a +2 charge on the reactant side and a +3 charge on the product side. So the only way I can fix that is adding electrons. So where would I put an electron to fix that? That would be on the product side. You can see now I have 3 pluses and 1 minus, which gives me a 2+ charge on my product side and a 2+ on my reactant side. Let's talk about the reduction. I have 8 pluses with the hydrogen, and I have 1 with the permanganate, 1 minus with the permanganate. That's a total of 7+. Okay, I have 8 pluses and 1 minus. That's a 7+. On the product side, I have 2+ from the manganese, and water has 0, so we have 2+. I have 7+ on the reactant side, 2+ on the product side. I need to balance that. The only way is to add electrons. So I'm going to add electrons to the reactant side, 5 of them. That way, that gives me a total of 2+, which is equivalent on both sides now. Notice a check is that when it's an oxidation, your electron should always be on the product side. If you're reduction, your electron should always be on your reactant side if you're doing things correctly. Now that I have my 2 half reactions, I need the whole reaction to be balanced. So I need to add some make sure the number of electrons cancel. Okay? So, since I got 1 being produced and 5 taken on, I'm going to go ahead now and balance it by making the iron oxidation go 5 times. So everything's multiplied by 5. That gives me 5 iron 2s, 5 iron 3s, and 5 electrons. After that, my electrons cancel. And now I can bring down everything. Which means I have 8 pluses, 1 permanganate, 5 iron 2s, 1 manganese 2, 5 iron 3s, and 4 waters. At this point in time, it's a balanced ionic equation, which means I can check it and see that all my atoms are balanced and all my charges are balanced. I also got to make sure that I have it in the lowest whole number ratio and that I have nothing in common on both sides that I can cancel. Looking at it, there's nothing the same on both sides, so I don't have anything I can reduce there, and I have odd and even numbers, so there's no number I can divide by to reduce it any further. So this is my balance equation. Let's check it though, just to make sure it's right. If I did do things, then all my atoms should be balanced and all my charges should be balanced. I see that I have 8 hydrogen, 8 hydrogens. I see I got 1 manganese. I see I have 4 oxygens. And I see I have 5 irons. So all my atoms are balanced. Okay, what about charge? I see I have 8 pluses and a minus, that's 7 pluses. And then I have another 5 2s, that's 10 plus, that gives me 17 plus. On the other side, I have a 2 plus, 5 3s, which is 15, and 2, that's 17, and 0 on the water. All of my atoms are balanced, as well as my charges. This is a little bit more difficult of a problem. Here is a molecular equation where I'm going to have to get to the net ionic before I can actually balance the redox. You can see I have several oxygens on both sides and chlorines. So balancing this by inspection would be slightly difficult. Okay, so using the procedure of balancing a redox will make this easier by using the half reaction method. So let's first write the net ionic equation. I got potassium permanganate. That's a soluble salt. So what happens to a soluble salt when we place that in solution? It ionizes 100%. So that means I have potassium ions and permanganate ions. Let's look on the product side and see if I can find where potassium is. And we find it underneath with the potassium chloride. Well, what's that? That's a soluble salt. What happens there? Breaks up into ions. Potassium ions and chlorine ions. So potassium went from an ion, K plus ion, to a K plus ion. Nothing happened chemistry-wise. Therefore, that's a spectator. So I'll just get rid of that and not bring it down to my net. Let's look at the permanganate. I got MnO4 minus, and on the other side, you see it's part of manganese 2 chloride. Okay, that's a soluble salt, so it breaks up into manganese 2 and 2 chlorine ions. Well, going from MnO4 minus to Mn2 plus, that's chemistry. That's not a spectator. So we'll bring that down to our net ionic equation. Let's look at the sodium nitrite. Okay, looking at sodium nitrate, that's a soluble salt, breaks up into sodium and nitrate ions. Let's find sodium on the other side. It's part of sodium nitrate. Soluble salt, breaks up into ions, sodium ions and nitrate ions. Well, it's Na plus on the reactant side, Na plus on the product side, no change, that's a spectator. I'll get rid of the sodium. NO2 minus, your nitrite, went from that to NO3 minus on the product side. Therefore, there's chemistry going on, so that's not spectators, so we'll go ahead and bring those down. Last species is HCl. That's a strong acid. What happens to strong acid? Ionizes 100%, so I got H pluses and Cl minuses. Let's see if we can find the H plus on the other side. We see it's part of water, so it went from H plus to H2O. That's chemistry. Therefore, I need to bring that down. It's not a spectator. It is chemistry. So what I have left now is chlorine. Okay, so I got Cl minus on the reactant side. On the product side, we got Cl minus because that's a soluble salt, and we got Cl minus. That's a soluble salt for the potassium chloride. So Cl minus in all cases, it's exactly the same. That's a spectator, so I'll get rid of all the spectators. So there's my net ionic equation. That's what I'm going to use to go on forward for my redox. A couple things to note here. Number one, notice that it has H plus and H2O. That's an indication of acidic solution. Okay, I'm not going to use that in my half reactions to start with. I'll put them in later as I need them to balance things out. Other thing I want you to notice, if you go back up in the original equation, did you notice something about that KCl? What did we do? We eliminated both as spectators, the potassium as well as the chlorine. Okay, you need to put that back on your equation when you finish at the end. Okay, if you don't, it's not going to be balanced. But as long as you're checking your work at the end, you're going to see you need it. If you're going fast and just put an answer and not paying attention, you could get it wrong. So I like to just say, okay, let's circle it since the whole thing went out and bring it all the way down here to kind of remind me that I got to put it back in. Okay, so let's go ahead and continue on. First off, I got to figure out what's being oxidized. Okay, if you look at NO2 minus going to NO3 minus, the charge on that nitrogen and that NO2 minus got oxygen at -2, two of them that's -4. What -4 equals -1? That would mean that nitrogen here is a +3. NO3 minus, you got 3 -2s, that's -6. Nitrogen -6 equals -1, that would be 5 plus. So it's going from a 3 plus to a 5 plus. That's an oxidation. You also could determine that by going from NO2 minus to NO3 minus. It stayed the same charge. All it did was add an oxygen. Therefore, the charge on that nitrogen had to go up by +2 to keep that working. So there is my oxidation. I'll bring that down as my oxidation. What's being reduced? Well, it's very similar to the one we just did on the last slide. We got permanganate going to manganese 2. So you got Mn plus 7 going to Mn2, or look at it in point of view of I'm losing oxygens, therefore that is a reduction. Okay, next thing we're going to do is balance atoms. Let's handle the oxidation first. Got 1 nitrogen on both sides, not a problem. I got 2 oxygen on one side, 3 oxygen on the other side. If I try to change that by using what's there, I would never catch up because I would mess up the nitrogens once I balance the oxygens. So I have to use something from outside, something external, which is going to come from that water and H plus. Since I need an oxygen on the reaction side, that's the side that I'm going to add a water. Okay, how many? Just 1, because I only need 1 oxygen, so that gives me 3 oxygens on both sides now. But now I have a hydrogen problem, so I'll fix that by adding 2 H pluses to the product side. So now my atoms are balanced. The reduction, I got MnO4, got manganese on both sides, not a problem, but I have an oxygen problem. I need 4 of them, so I'll go ahead and add 4 waters to the product side. Then I'm going to add 8 H pluses to the reactant side. Now my atoms are balanced. Let's talk about charges. For the oxidation, I have water, which is neutral, it has 0. I have NO2 minus with 1 minus. Therefore, my total is 1 minus on my reactant side. On the product side, I got 1 minus from the NO3. And I have 2 pluses. So 1 minus and 2 pluses gives me a 1 plus on my product side. The only thing I have at my disposal is electrons, so I'm going to have to add 1 electron to the product to get it to 0 and another electron to get it to minus 1. So I end up adding 2 electrons to my product side. The reduction, my total charge on my reactant side is 7 plus. 8 pluses and a minus makes 7 plus. On the product side, I got 2 plus. So I'm going to add 5 electrons to the reactant side. Now I have 2 balanced half reactions. I need the whole thing to balance. So I will multiply my oxidation by 5 and my reduction by 2, giving me a common thread of 10 electrons. So my 10 electrons will cancel out. And then I have to bring down everything else. Make sure I got to multiply that 5 times everything. 5 waters, 5 nitrites, 5 nitrates, 10 H pluses. Same thing with the reduction. Bring all that down. It gives me 2 permanganates, 5 nitrites, 16 hydrogen ions, 5 waters, 2 manganese 2s, 8 waters, 5 nitrates, and 10 hydrogen ions. Okay, this is my balanced net. I need now to check to make sure it's not divisible by some number or I have things in common on both sides. Well, what jumps out at me is I do have some things that are common on both sides. I have 16 H pluses and 10 H pluses. So 10 of them are basically canceling out and I have an excess of 6 on the reactant side. So I will cancel out my 10 of those H pluses and leave me 6 H pluses, hydrogen ions. And I also have the same thing with waters. I have 5 waters and 8 waters. That means 5 of them are canceling on both sides, leaving me an excess of 3 waters on my product side. Give me my balanced net equation as written. At this point, I can verify that everything is balanced. Let's check out the atoms first. I got 2 manganetes and 2 manganetes. I have 8 oxygens plus 5 to 10 oxygens. That's 18 oxygens. On the product side, I have 15 oxygens plus 3 oxygens. That's 18 oxygens. I have 5 nitrogens and 5 nitrogens, 6 hydrogens, and 6 hydrogens. All the atoms are balanced. Let's check charges. I got 2 minuses for the permanganate. I got 5 minuses for the nitrite. That's 7 minuses. And I have 6 pluses. 7 minuses and 6 pluses gives me a total of 1 minus. On the other side, I have 2 2s from the manganese 2. That's 4 pluses. And I have 5 minuses. 4 pluses and 5 minuses gives me a total of 1 minus. Balance. So my atoms and charges are balanced. This is a balanced redox. However, we're going to go one step further because remember this was a formula unit equation. Okay, this was a molecular equation, so I need to go back and put back the spectators. So I got permanganate first. I had potassium. I got to put potassium together. When I do that, that's not going to change my coefficient. It'd still be 2. My potassium's plus 1. My permanganate's minus 1. So therefore, it's a 1-to-1 relationship. Putting back to my formula. Let's look at nitrite. Same thing. Sodium is a plus 1, so it's going to be sodium nitrate. So I would bring down my 5. H plus, the spectator ion, is my chlorine. So I'll bring that down. And once again, I have bring down my coefficient. No change there. There's no subscript change in the number of H's, so I bring down my 6. The manganese 2, chlorine is my spectator. I got to put 2 Cl's on there, but that doesn't change the number of manganese, so we bring that down just like it is. 2 MnCl2s. Water will come down just like it is. And now I have nitrite. nitrate rather, I need to now add my sodiums, and once again 1 to 1, therefore it comes down 5 sodium nitrates, which looks like my balance equation. However, if you were to turn this answer in, it'd still be wrong. Why is that? Well, it's not all balanced. There's some things that are missing. Remember that KCl, okay, that I told you had to put back in. Okay, we need to balance the potassiums and chlorines. If you look on the reactant side, I have 2 potassiums, but there's no potassiums on the product side, so I need to fix that. So we'll go ahead and put in that KCl. Now the question is, how many KCl's? Well, I need 2 potassiums. There's none on the product side, therefore it's got to be a 2. Now hopefully that fixed my chlorine. Let's see if it does. I got 2 chlorines. I have 2 chlorines. Okay. I have 2 times 2, that's 4 chlorines. That's a total of 6 chlorines on this side, my product side. And I have 6 chlorines on the reactant side. So that's balance. This is my balance equation. The last example I have has to do, it's also a net ionic equation. It has charges, so you have to do it by balancing redox. But notice it has an OH minus on it. That's an indication of a basic solution, which is a case of using OH minus in water at our disposal to balance it out. So I need to figure out what's being oxidized and what's being reduced. Well, if you look at your chromium 3 iodide, okay, we know that chromium here is a +3. I minus, there's 3 of them, so it has to be +3. On the other side, you see that chromium now has 4 oxygens at -2. That's -8. So chromium -8 equals a -2. That means that this is a +6. So it goes from +3 to +6. That's an oxidation. You also notice that there's no oxygens on chromium 3 iodide, and there are oxygens on chromate. Therefore, that is an oxidation process. But let's look at that iodine a little bit further. You get iodide, which is a -1. Okay, what is it on the other side, on the product side? Well, I got 4 oxygens at -2. That's -8. So your iodine -8 equals -1. That means it's a 7+. So you have your iodine going from -1 to 7+. That's an oxidation. Also went from no oxygens to 4 oxygens. So you have 2 species being oxidized. Can you have more than 1 species being oxidized or reduced? Yes, you can. You just got to bring them all down on that same oxidation line. So we'll go ahead and do that and bring those down. The whole thing. The CRI3 going to the CrO4 2- and the IO4-. Let's see what's being reduced. You got Cl2, which is your elemental state of chlorine, which is a 0 state, going to Cl- on the product side. That's a reduction. So I'll bring that down. The next thing that we need to do is to balance our atoms. So let's do that. Let's handle the oxidation first. I have 1 chromium on both sides, not a problem. I have 3 I's on my reactant side and 1 I on my product side, so I need to fix that by putting the 3 in front of my periodate. And now let's check the oxygens. You see I got 3 4s, that's 12 oxygens, and another 4 from the chromate. That gives me 16 oxygens. Okay, so I need to balance that by putting oxygen on the other side. Well, since it's basic, we said we use OH minus in water at our disposal. And we said if hydrogens are not an issue, you can do a 2-to-1 ratio between your OH minus and water. So we got 2 OH minuses for every water. So you're going to say, okay, let's put 16 OH minuses for that 16 oxygen missing, and then you would also add 8 waters to the other side, okay, to get that 16 hydrogens that you just added to balance out. But what did you notice happened in the process is that I added 8 more oxygens. So I got the 16 to start with plus my 8 from here. So it's not 16 oxygens, it's 24 oxygens. So I need to change this now to 24. Okay, well when I do that, then I'm going to have to change this to 12 waters. Well, I'm now off by 4 more oxygens. Okay, so I'm going to have to change this again. It's now 28 oxygens. I'll come back here to 28 OH minuses and 14 waters. Okay, as I said earlier when we're talking about the rules, I know that this is going to happen, so instead of going back and forth, which you're going to go back and forth another 2 times before you get to the correct answer, anytime my hydrogens are balanced and I'm trying to balance my oxygens in my basic solution, I'm going to basically say, okay, how many oxygens do I need? Okay, in this case, I needed 16 oxygens. I'm going to double that, okay, and add half as many waters to the other side. So I add 32 OH minuses and 16 waters. That way my hydrogens will stay balanced and my oxygens will be balanced. Okay, so I'm taking into account that I know it's going to happen, so I'm doing it already. Now you can go the other way if you want, back and forth, and it may take you several times, but you eventually will get to 32 and 16. Okay, we now got to balance the redox one. I got 2 chlorines on one side and 1 on the other, so I just need to put a 2 in front of that chlorine ion. Now that atoms are balanced, I have to balance charges. On my oxidation, the total charge on my reactant side is 32 minus, okay, all coming from the OH. On the product side, I have 2 minuses and 3 minuses, so that's 5 minuses. So I need to balance that off. They're off by 27, so I'm going to add 27 electrons to my product side. Remember, oxidation should be on the product side. That's an indication I'm doing things right. So I got my 27 electrons and my 5 minuses. That gives me a total of 32 minuses on both sides. The reduction, got a total of 0 on my reactant side and 2 minus on my product side. So I need to balance that by putting 2 electrons on my reactant side, which makes sense because it's reduction. Okay, now I have my 2 half reactions balanced, but I need to bring them together. So I need a common factor. Simplest thing over here would be cross multiplying, so I'm going to end up doing 2 times my oxidation and 27 times my reduction, which then would cancel out my 54 electrons in both cases. And then I need to bring down the rest of the stuff, which means I have 2 times 32, which is 64 OH minuses, 2 times my CRI3, and then 27 times my Cl2s. On the product side, 2 times my chromates, 6 times my periodidates, 2 times the 3, 27 times the 2, 54 for my Cl minus, and my 32 waters, 2 times the 16 water. Now I got to check to see if there's anything that I can reduce on both sides, and there's nothing reducible that's in common on both sides, and it's not divisible by any number because it's odd and even numbers. So this is my final answer. So all my atoms should be the same number on both sides. If you check it, they are 64 oxygens, 64 oxygens, 64 hydrogens, 64 hydrogens, 2 chromiums, 2 chromiums, 6 iodides, 6 iodides, 54 chlorines, 54 chlorines. All the atoms are balanced. As for charges, you got 64 minuses. So I got 64 minus on this side. I have 2 minuses, that's 4 minus, 6 minus, that's 10 minus, 54 minus, that's 64 minus. Now that we've refreshed our memory on balance and redox, let's balance the redox equation involved in experiment 16. We have thiosulfate reacting with iodine. In this reaction, we need to figure out what's being oxidized and what's being reduced. Looking at this, we see that thiosulfate is being oxidized, so we bring that down. And we see that iodine is being reduced. It's going from a 0 state to a -1. Next thing we have to do is we need to balance the atoms. We see for the oxidation that I got 2 sulfurs on the reactant side and 4 sulfurs on the product side. So we're going to have to multiply the reactant side by 2. And when we do that, that balances the atoms. I have the same number of sulfurs and oxygens on both sides. For the reduction, I can see that I need to add a 2 on the product side to get the balance of the atoms. Now I need to make sure that my charges are balanced. We see on the oxidation that the reactant side I have 4 electrons, 2 times that -2. And on the product side I have a total of a -2. So to balance this, I need to put 2 electrons on my product side, which makes sense since it's an oxidation. On the reduction, I have 0 electrons on my reactant side, and I have 2 negatives on my product side. Therefore, to balance this, I need to put electrons on my reduction side, my reactant side, 2 of them, which makes sense since it takes on electrons, to balance this out. Notice that the electrons are the same, therefore I don't need to multiply by any factors, so therefore my electrons will cancel out, and I have my balance equation. Now, this is the same procedure you're going to use to balance all the equations, and we have several of them, 24 of them, assigned in the lab manual. Okay, and outside exercise page 189. I have the answers posted on my website, so you can go see them there. Basically, you need to work those problems. It gets better with practicing redoxes to get the correct answer. You can't just memorize them. There's a million of reactions. Those are just 24 of them, so you need to be able to work them. As you take time working them, you're going to get easier and easier as you go. You need to know some information, solubility rules, charges. You have to have that in your head to be able to balance equations. This is an important part of your lab grade. It's about 10% of your grade. You have a redox quiz that's coming up in about a month. Okay, so you need to be working on this along the way. This is not something you can do the night before. If you do not do the redox information, then you're probably going to end up losing about a letter grade on your final grade. Zeros are possible on this redox quiz. Okay, you have to demonstrate that you know something about balancing a redox. Now, from this information above, we can determine our number of equivalents per mole of substance. We can see there's 2 electrons for every 2 moles of thiosulfate, so there's a 2-to-2 ratio, in other words a 1-to-1 ratio between our thiosulfate and electrons. So the molarity will equal the normality in that case. And for our iodine, you can see there's 2 equivalents for every 1 mole of iodine. Therefore, the normality is going to end up being greater than the molarity. Okay, or another way of looking at it, your molarity will be 1/2 the normality. Okay, so basically we said thiosulfate, there's 2 equivalents for every 2 moles of thiosulfate, which ratio-wise turns into 1 equivalent for every 1 mole of thiosulfate. So that basically is saying that my normality will equal my molarity. For the iodine, there's 2 equivalents per 1 mole iodine, which came from that equation. So basically what we're saying in that case is that our normality, 1/2 the normality, will equal to the molarity. Okay, or another way of looking at it, normality will equal to double the molarity. Now for the experiment, we're going to do the standardization first. We're going to standardize the thiosulfate against 0.1 normality of iodine standard solution. The changes in this experiment are as follows. All right, we're going to use 10 milliliters of iodine, 30 milliliters of deionized water, and 1 milliliter of starch. That's about 20 drops. Okay, so those are the changes from the procedure. We're changing different volumes again. Starch indicated, it's going to say in the manual to add it somewhere later after it turns a pale yellow. Okay, don't worry about that, just add it from the beginning and it still works out fine. So we can add the starch from the beginning. When you have starch plus the iodine, which is going to give us a blue color. So any blue color shows that there's iodine in that solution. Our goal is to get rid of all that iodine. Okay, so when all the iodine is gone, then you're going to have a colorless solution. Okay, so after the reaction has occurred. So at the end point, when all that iodine is consumed, we're going to have a colorless solution. So what we're doing is going from a blue color to colorless. So when we go from that one drop from blue to colorless, that's where we reach that equivalence point, that end point, okay, of observation. Now, one word of note here is colorless means lack of color. Okay, colorless does not mean clear. Clear means transparent. Something can have color and still be called transparent. Colorless means lack of color. We're looking for no color in that solution. Since we're doing normality, we have a simple calculation, which is just NV equals NV. So in this particular case, for the standardization, we know the normality of our iodine. We know the volume of the iodine. We're finding the volume of the thiosulfate from our titration, how many milliliters it took to get to colorless. So then we can calculate the normality of our thiosulfate. Now we want to do this several times. So we're going to do a minimum of 3 runs again. We want to get within plus or minus 0.05 normality. Okay, that's about 0.5 milliliters difference between your samples. Okay, if you have this, then we're going to call that a standard solution. And then we plan on reporting our average normality plus or minus the standard deviation. Anytime we got 3 or more runs, I want a standard deviation of thiosulfate ions. This is our standardized solution. This is the value we're going to use to do our unknown. One other thing I expect you to do is convert your average normality, okay, to molarity. Okay, I want you to calculate your average normality to molarity. Okay. Now, realize since we're talking about thiosulfate, which is a 1-to-1, 1 equivalent for 1 mole, means it's going to be the same numeric number. Second part of the experiment, we're going to do exactly the same procedure as the standardization, except now we're going to use an unknown concentration of I2, and we know the concentration of our thiosulfate from the standardization. Once again, we're going to do a minimum of 3 runs, plus or minus 0.05 normality, somewhere around 0.5 milliliters is what we're looking for. You will be reporting the average normality, plus or minus the standard deviation of normality, of iodine unknown solution. Once again, I'm going to want you to convert your average normality to molarity. Okay, remember in this case that it's 2 equivalents for 1 mole of iodine, so therefore your molarity will end up being 1/2 the concentration of the normality. Okay, so molarity and normality is not equal for your iodine. How much chemicals do we need? Well, for the thiosulfate, in the form of sodium thiosulfate, we need about 150 milliliters. For the 0.1 normality of your standard solution, you need about 50 mils. In your unknown iodine solution, you need about 45 mils. And that will be assigned to you from your TA. Give you an estimate of endpoints. For the standardization, your endpoint will be approximately 10 mils. So you know you can add about 8 and then slowly creep up on it. For the unknown, your unknown endpoint would be somewhere between 3 and 12. So you can't really go too fast on the first one. You're going to add 1 or 2 mils, slow down. And then when you know where that endpoint is after the first one, you can go a little faster.